So we have a notation. Okay, so this is a curly D, and it is not a straight D, and it is not a delta. It's a D that kind of curls backwards like that. And the way you read this symbol is partial. Okay, so it's the special notation for partial derivatives. And essentially what it means is we are going to do a derivative where we care about only one variable at a time. That's why it's partial. It's missing the other variables. Okay, so a function of several variables doesn't have a usual derivative. It has only partial derivatives for each variable. So the partial derivative, df partial f partial x at x0, y0 is defined to be the limit when I take a small change in x, delta x, of the change in f divided by delta x. Okay, so here I'm actually not changing y at all. I'm just changing x and looking at the rate of change with respect to x. And I have the same with respect to y. Partial f partial y is the limit, so I should say at a point x0, y0, is the limit as delta y tends to 0 of, so this time I keep x the same, but I change y. Okay, so that's the definition of a partial derivative. And we say that a function is differentiable if these things exist. Okay, so most of the functions we'll see are differentiable, and we'll actually learn how to compute their partial derivatives without having to do this. Of course, we'll just use the usual methods for computing derivatives. So in fact, I claim you already know how to take partial derivatives. So let's see what it means geometrically. So geometrically, my function can be represented by its graph. And I fix some point x0, y0. And then I'm going to ask myself what happens if I change the value of, if I change the value of x, keeping y constant. So if I keep y constant and change x, it means I'm moving forward or backward, parallel to the x-axis. So that determines for me a vertical plane, okay, parallel to the xz plane when I fix y equals constant. And now, if I slice the graph by that, I will get some curve that goes, it's a slice of the graph of f. And now, what I want to find is how f depends on x if I keep y constant. That means it's the rate of change if I move along this curve. So in fact, if I look at the slope of this thing, so if I draw the tangent line to this slice, then the slope will be partial f over partial x. I think I have a better picture of that somewhere. Yes, here it is. Okay, that's the same picture, just with different colors. So I take the graph, I slice it by a vertical plane, I get a curve, and now I take the slope of that curve, and that gives me the partial derivative. And to finish, let me just tell you how, and I should say partial f partial y is the same thing, but slicing now by a plane that goes in the yz directions. Okay, so I fix x equals constant. That means I slice by a plane that's parallel to the blackboard. I get a curve, and I look at the slope of that curve. Okay, so it's just a matter of forgetting one variable, setting it constant, and looking at the other one only. So how to compute these things? Well, we actually, to find, oh, there's a piece of notation I haven't told you yet. So another notation you will see, I think this is what one uses a lot in physics, and this is what one uses a lot in applied math, which is the same thing as physics, but with different notations. Okay, so there's two different notations, partial f, partial x, or f subscript x, and they're the same thing. Well, we just treat y as a constant and x as variable. And vice versa if we want to find partial with respect to y. So let me just finish with one quick example. Let's say that I give you f of x y equals x cubed y plus y squared. Then partial f partial x, well, let's take the derivative. So here it's x cubed times a constant. Derivative of x cubed is 3 times x squared times the constant, plus what's the derivative of y squared? 0, because it's a constant. If you do instead partial f partial y, then this is actually a constant times y. The derivative of y is 1, so that's just x cubed. And the derivative of y squared is 2y. Okay, so it's fairly easy. You just have to keep remembering which one is a variable, which one is not. Okay, so more about this next time, and we'll also learn about maxima and minima in several variables.